Greetings, this is Shannon Malchick-Myers recording in beautiful San Diego, California. Today we'll be talking about how to test a claim about the difference between two means, mu1 and mu2, when they are independent samples. So sometimes we are interested in whether two means are significantly different, or in constructing a confidence interval estimate for the difference between two population means. The concepts are very similar to working with one sample, except you'll have two of each parameter and statistic relating to each sample and population. Previously, we were working with an example relating to the mean jockey weight at Del Mar. For this section, let's extend this scenario to include a sample of the mean jockey weight at Churchill Downs. These samples were obtained on the same day, so they are independent samples. But first, as always, some essential ingredients. Mu1, mean of the population which sample 1 is drawn from. X bar is the sample mean, so it's the mean of sample 1, and symbolically you would just sum up all of the values and divide by n1, and jumping down there, n1 is the sample size of sample 1. And then S1 is the standard deviation of sample 1. And then, of course, mu2, n2, x bar 2, and s2 will all apply to population 2. So the standard error of the difference between the two sample means is going to be your t star. We're also assuming, of course, that sigma is unknown. That's the more realistic situation. And then you multiply this by your standard deviation squared from sample 1 over n1 plus your sample standard deviation s from sample 2 squared over n2. And your confidence interval will just be x bar 1 minus x bar 2 plus or minus the standard error of x bar 1 minus x bar 2. The test statistic that we'll be using is a t statistic, and it's going to equal to x bar 1 minus x bar 2. If you want, you could put in a minus 0 there if you'd like. The assumption under the null is that mu1 minus mu2 is 0. And that's over the standard error of x bar 1 minus x bar 2. Your degrees of freedom are just going to be n1 plus n2 minus 2. That's because we used the sample to estimate two standard deviations. So you add the samples together and then take away the number of parameters that we estimated by using the sample. Okay, there's like a complicated formula you can use and that your calculator will use, but this is kind of a good rough estimate of your degrees of freedom for this test. Okay, so the requirements are that the sample data are from 2 simple random samples that are independent. And both data sets have a roughly normal distribution. So you can check the histograms, or a sample size greater than 30. That's kind of a sort of a baseline. You just have to use your best judgment. All right, caution when testing a claim about 2 population means. The null hypothesis is that the difference of the 2 means is 0. And the decision to reject or fail to reject the null will be based on. So here, your null, H0, would be mu1 minus mu2 is 0 versus your alternative, which would be mu1 minus mu2 is not equal to 0. So here, what we would be looking at is a good 2-tailed test. And that means what? That if you construct a 95% confidence interval estimate, that will be the equivalent of testing at or it will have the same t-star as testing a 2-tailed test at the 5% level. Very good. All right, so critical value method, reject the null if the test statistic falls into the critical or rejection region. Set by plus or minus t star, which is, determined by the alpha level. P-value method, reject the null if the probability of obtaining a test statistic at least as extreme is less than the alpha level. The confidence interval method, reject the null if the interval of likely difference values does not include good 0. All right? Okay, so let's look at an example. We'll come back to the racetrack. This is I think the same sample I used in the last video, so you may remember it. If not, that's fine. We'll be looking at it again. And here's another sample from Churchill Downs. Okay, so I've entered in the first list already, and under list 2, we'll go ahead and we'll enter in the second data list. That would be the height, of the jockey heights from Churchill Downs. All right, so I'm just entering them in, so you can go ahead and do that too, and have fun. We need to make sure that we look at the histograms of, each of these lists, or the data in each of these lists. So what I'm going to do is I'm going to go to stat plot. I'm looking at the very first one, and it's got already our list, and so we can make our histogram whatever we want, whatever color. So let's look at the graph. And this one is roughly symmetric, so we're good to go there. So I need to change this into the type of graph that I'm interested in. And so I want the histogram, and so we're good there. And then we may also want to look at our window. Let's just double check our window. And we certainly don't need our x minimum to be at negative 1500-ish. So x minimum, why don't we put at 0? X maximum, I don't know, 65. And then our y minimum could be 0, and our y maximum, let's make it 5. And now we can graph it. All right, so that gets us at least close to it. And you see this one here? We've also got a roughly symmetric graph going on. So that was the first part. We had to make sure we had symmetry. Now next up, what we need is we need to calculate our one variable statistics. So if we go to the stat menu, we will have calculate one variable stats, and then to get list one, we'll hit second L1 in this calculator and enter. And look, we've got all the stuff that we need. Stat, calculate, we're going to do one variable stats, and this time we're going to go to list 2. And now we have our stats for list 2. Okay, so here we've got the graphs showing that we've got roughly symmetric histograms, and we also have the one variable statistics for each of these. And so now what we'll do is we'll use these to find our confidence interval and test statistic, okay? Okay, so now let's do our thing. Remember that the confidence interval in general is x bar 1 minus x bar 2 plus or minus the standard error of x bar 1 minus x bar 2. Well, x bar 1 was 61.2, x bar 2 is 60.5, and then plus or minus our t star. So we're going to have to go look that one up. And our t star will be multiplied to our S1, which was 1.55-ish, squared over N1, which is 10, plus S2 squared, which is the 1.58 approximately, over N2, which is 10. We need to look for the 0.975 area, and we need to do that under distribution. So remember, we're going to inverse t. The probability is 0.975, and our degrees of freedom, we said we're 18. And we get 2.10. 2.10 times all that. And then computing everything on the calculator, let's see. This will be 0.7, I believe. And then plus or minus, coming back here, we'll say 2.10 times second square root. And we had, what, 1.55 squared divided by 10 plus 1.58 squared divided by 10. And let's see here, I get about 1.45. No, sorry, 1.47. We don't need that one. 1.47. Okay, so my interval of likely values will be, if I subtract, you see I'll get, okay, so this will give us let's see, negative 0.77 is less than mu1 minus mu2, which will be less than, let's see, if I add, I'll get about 2.17. At the 95% level of confidence, sorry, the difference between the mean jockey heights at Del Mar and Churchill Downs on opening day is between negative 0.77 of an inch and 2.17 inches. Cool, cool? So what does that mean? That we'll probably we'll fail to reject the null because a hypothesis for this next one, because this test at the 5% level, as you can see for the confidence interval part, you would say, oh, well, 0 is one of the likely values and therefore we'll fail to reject the hypothesis that the two means are different. First of all, let's look at the how to go directly to the confidence interval here. Stat, so we just go straight to stat, test, and we have a 2-sample t interval. And look, we've got all of our data. You just double check that the confidence level is right. You can make sure the lists that are showing up are the same. And we are not pulling our standard deviation. Okay, so there's all your screenshots. There we go. Cool, cool. So, all right, let's run our other tests. So, null and alternative hypotheses. The null is that mu1 minus mu2 is 0. Versus the alternative where mu1 minus mu2 is not equal to 0. Find the test stat. Well, remember we do t is equal to x bar 1 minus x bar 2 minus 0 if you need to. And then divided by the square root of s1 squared over n1 plus s2 squared over n2. Well, that will equal to, so you'd have 61.2 minus 60.5 divided by the square root of approximately 1.55 squared over 10 plus approximately 1.58 squared over 10. Dogs are after someone. And that will be 1.00. So critical value method, you'll have your, remember you'll have your fatter tails, something like that. And then you down here is our t-axis. This is 0, 1, 2, 3, -1, -2, -3. Okay, so your boundary values here, we had found the T star, remember, for your confidence interval. And we had found T star to be, sorry, I never quite did this one. Finished that. We wrote it down here, but I didn't finish it. That was 2.10. Okay. So we have a two-tailed test here. 2.10 for our boundary values is going to be around here. And -2.10 would be on the other side. And so in the purple region here, we would have our rejection region. So now when we put where our test statistic is, it lies right here. Remember, at t = 1. And so here, this definitely, t = 1 does not fall into this rejection region, right? At all. So we, based on that, would fail to reject the null. All right, so our p-value method, we would write, kind of looks similar, remember? Again, we're going to have fat tails, roughly, something like this. And this is our t-axis. And our test statistic was t = 1. And remember, we need to find the probability. We got a positive test stat. So we basically want to find the probability of this region. And then what we're going to do is double it to get the p-value. So 2 times the probability that t is greater than 1 is our p-value. And that's going to equal to 2 times second distribution. We would have t-CDF. Our lower bound is 1, if you want, 0.00, comma, the upper bound, let's just put something really big, 100, and then our degrees of freedom were 18. And so we get 2 times 0.1653. So that'll be about 0.3306, I think, right? Which 0.3306 is definitely greater than alpha, which was 0.05. So again, we fail to reject the null. So if you go now to stat test, and if you go to sample t-test, oh, lo and behold, let's see what we get. Pretty good, all right? Notice their different degree of freedom, but this is a real good visual for what all we just did. So in conclusion, we would say at the 5% level, there is not significant evidence to reject the claim that there is no difference in jockey height at Del Mar and Churchill Downs on opening day. That should be mean jockey height. All right, I hope you have a fabulous day, and I'll talk to you soon. If you like the video, don't forget to subscribe. Bye.